coats, and silica film. Can you open? Is it? Did you find it all? So the task is to calculate the amount of silica film needed for complete consumption of portlandite. So how much silica film you should put in your cement to fully deplete portlandite. This is the task. And for that, you start with the Portland cement, hydrated cement paste has 27% of portlandite. This is like a, typical value. This is the amount of portlandite that you produce when you react cement. You also saw it in the slides, maybe around 20 to 25, 27, 23. Yeah. This is maybe more for C3S, it's a higher amount of portlandite. So you can also change, depending on the cement, you can also change this value. So first we write the reaction. The assumption is that our CSH is calcium silica ratio of 1.3, and then you can, the stoichiometric coefficient here, 1.3. And the other thing is to consider the degree of reaction. So in the task, I also added that only 40% of the silica film is reacting, because not all of the silica film reacts. And then you can start your mass balance calculations. Maybe I can write it. Let me write it. There was. Okay. Let's do the writing. So we have the Puzzolanic reaction. That CH plus silica film, which is S, plus water gives us CSH. Actually, we want to say exactly. And we know typical Puzzolanic reaction product is 1.3. And then we can balance this. So we want to know how much silica film we can add to fully consume for stoichiometric reaction, and the degree of reaction for the silica film is 40%, 0.4. So the question is the mass of, we want to know the mass of portlandite, no, the mass of silica film that we need to put in our cement paste to fully consume portlandite. And for that we know from the cement reaction that we are producing 0.27 grams of Portlandite per gram of cement. So this is given, and now we want to calculate this. So if you remember, we need to know we are calculating the mass of silica film from the stoichiometry. So we always we start with stoichiometry, and the stoichiometry is that the mass of silica is we said that we need the molar masses always, molar mass of silica times the stoichiometric coefficient of silica, which is 1, divided by, or we can put n, I don't know, sometimes it's mu, divided by the molar mass of CH times the stoichiometric coefficient of CH. So this is always the same stoichiometry, you just do molar masses and you should put the stoichiometric coefficients. And then this will give you the unit of, what will be the units here? This will give you units of grams of silica fume per gram calcium hydroxide. But we know that we have 0.27 gram of Portlandite per gram of cement. So if we multiply here, or we do mass of silica fume, if you want per gram of cement, then we just multiply by the amount of Portlandite, by this amount. Let's call it this is then the mass of Portlandite in cement. So if we just have gram per gram of Portlandite, and then we multiply it by the mass of Portlandite in cement, we get the unit of gram of silica fume per gram of cement, right? So this is what we want. How much silica fume per how many grams of cement. So it's just very simple stoichiometric formula. You can calculate this. And this is what I implemented in Python. You just need molar masses, stoichiometric coefficient, and you can calculate. Any questions here for this example? You can do the same stoichiometric calculation for any degree of reaction or any, you can also ask yourself, if I put, what is the degree of reaction if I put 10% of replacement and I have so much Portlandite in cement in reference, what would be the amount of Portlandite in your cement paste? Which is basically then you can compare directly with your thermogravimetric measurements. Or if you compare with your thermogravimetric measurements and then you can fit this degree of reaction. Here we actually are missing degree of reaction. You can basically determine the degree of reaction inversely from this model, just fitting your results from TG. Let me see, we missed here the degree of reaction, so we should multiply, of course. No, we should divide, because if you have less reacted, it should be, so this is the stoichiometric amount, and then if we want to put here, we should divide by the degree of degree of reaction of silica film. Because then we need more silica film, of course. So this is very, looks very simple to calculate, right? And you basically, from the thermogravimetry, you can now determine the degree of reaction of silica film. So if you go back to our Python code, let's see how you can calculate this. We just defined the degree of reaction of silica film, the mass of produced portlandite, 0.27 gram per gram of cement, molar mass of portlandite, molar mass of silica film. So those are the inputs. You can run this, and then these are the equations I just derived by hand. Basically, it's this. This is the most important, that the mass of silica film is the mass of silica film stoichiometric divided by degree of reaction. So if you divide by 0.4, you get a higher number. So you need more silica film. If it would be 50%, you divide by 0.5. So it's 2 times you need more silica film if you have only 50% reacted. And then this is the stoichiometric equation. Let me see. Yeah, it's not written. It's written, it's split it, but basically it's can I go back? No. Maybe here. No, I think my drawing is disappeared. But basically, yeah, the mass of the silica film is the molar masses of the silica film divided by the molar masses of the portlandite, which you can see here also. Let's see in the calculation. Maybe it's easier to see there. But there, actually, you need to solve the yeah, this is the calculation, and this is what you need to fix. So let's write it now together. So we had always use the molar mass. We have the molar masses here. So it's the ratio. Let me write the equation here. It's the molar mass of silica film divided by the molar mass. Later I will check what is the name of the variables. Let's just write the overall equation times the stoichiometric coefficient of silica film divided by the stoichiometric coefficient of portlandite. Always the same stoichiometric equation. Molar mass per gram of portlandite, so divided by the molar mass of portlandite. And then also multiply by the ratio of the stoichiometric coefficients. And then we said we need the mass of portlandite in cement per gram of cement, because we are calculating per gram of cement. This will give us per gram of portlandite, and here we have per gram of cement, and we just need to divide by the degree of reaction of silica film. That's it. Now let's take this, or if you, did you manage to type? So it's the ratio of the molar masses, silica film to portlandite, ratio of the stoichiometric coefficients, and then we get the mass of stoichiometric amount of portlandite per gram of, stoichiometric amount of silica film per gram of Portlandite just by doing the ratio of the molar masses and stoichiometric coefficients. And then this gives us the stoichiometric amount of grams of silica fume that reacts with Portlandite, so per gram of Portlandite. And then we multiply by how much Portlandite per gram of cement, then we get the unit per gram of cement. And we divide everything with the degree of reaction of silica fume, because then we need just more silica fume. Now let's see the real variables. So those are the variables. Molar mass CH, molar mass silica fume, okay, so let's put that here, molar mass MR, and then he already suggests you the variables. So the molar mass of silica fume divided by molar mass of Portlandite times the stoichiometric coefficient of silica fume was 1.3. Stoichiometric coefficient of Portlandite was 1. You can make a variable, but we can see it here. And then just we need a mass of Portlandite, which is the input, the mass of Portlandite, this one, and then we have the degree of reaction. So this is the mass of Portlandite and the degree of reaction. This is the variable. So this is the solution, fix me solution. The first part is the stoichiometry. I think now you really know it. The ratio of molar masses gives you the stoichiometric mass per gram of Portlandite. We did the same yesterday per gram of cement. Now it's just per gram of Portlandite. You should also consider the stoichiometric coefficients. It's not only the molar masses. And the new part now, because this gives you per gram of Portlandite, the amount of silica fume per gram of Portlandite, we need to know how much Portlandite per gram of cement, which is 0.27. And then we get the unit per gram of cement. And we should divide by degree of reaction, because then we need more Portlandite. And the unit is gram of silica fume per gram of cement. And from this, we already can calculate the replacement level. And the replacement, you know, that's very engineering calculation. The replacement fraction is just the mass of silica fume divided by 1 plus mass of silica fume, because 1 is the amount of cement. It's because it's per gram of cement. Everything is per gram of cement. So if you have the mass of silica fume divided by 1 plus mass of silica fume, you get the replacement level. How much cement can we replace by silica fume? So this then we can also write what is the mass of silica fume is exactly what we calculated here. So it's this mass of silica fume per gram of cement divided by 1 plus mass of silica fume divided by 1 plus mass of silica fume, exactly. And this gives you the replacement ratio of the fraction of the mass fraction of silica fume in cement. How much can we replace cement? Should we replace cement to fully react, to fully consume Portlandite? And now if we run it, we get the result. So we need more than 40% of silica fume. And if you remember our task, if you remember our slides, our experimental results from the slides, if we go here, so this is now a direct link to your experiments with TGA. If we go here, where was silica film? Yeah, here. Exactly. You can see 40% of replacement, and after 56 days, yeah, maybe if we leave it longer, it will be zero. Now it's less than 2.5% of portlandite. So it's actually quite good agreement. If you want, we can put the, you could almost calculate the exact amount of degree of reaction that we need to get not zero, but to get 2.5% of portlandite. This you just need to combine this example with yesterday's calculation of phase assemblage with, and then you can. Yeah, I think it's very easy also engineering exercise to calculate this. Any questions? So now we solved the first task. So those two are, you need to write those two lines. Did you manage to put these two lines to solve it? If yes, then I continue further. We can go to the second exercise, which is the metakaolin. So we can do the same calculation for the metakaolin. So you go to Google Drive. Again, this is the link I sent you, day 2, codes, stoichiometric, and then you take the metakaolin file, open it. And now we have the metakaolinite example. So it's the same example, we just did it now for aluminosilicate. This is the chemical composition of pure metakaolinite. Again, we assume that the degree of reaction is 0.4. We are writing the reaction, again 1.3 stoichiometry, assuming for CSH, and of course now we have also the aluminate and the typical reaction product of the metakaolinite putzolanic reaction is the strettlingite. This is the strettlingite. This guy is called strettlingite. C2ASH8. We could also have cache phase, of course, here, aluminate, but this is just simplified now. Example, I think in long-term reaction, this is the main phase, the most stable. So this is the first challenge for you to, write the reaction, then to do the balancing, which is easy in this way because here we have 1 alumina, here we have 1 alumina, here we have 1.3. Calcium plus 2 gives you 3.3. So now the stoichiometric coefficient is 3.3. Then we used exactly the same code. You just need to define the molar mass of aluminate, then the molar mass of metakaolinite. This is how it looks, the metakaolinite. Kaolinite has 2 molecules of water, and this is metakaolinite without water. So it's just AS2. And then, yeah, this is now we can see exactly again. From the stoichiometry, you want to know the mass of metakaolinite per gram of portlandite. So you always do the ratio of what you want to calculate. So you want to calculate the metakaolinite amount based on the known mass of portlandite. So you should put the ratio of these two. So the mass of the molar mass of metakaolinite, because we should work with molar masses, in ratio to the molar mass of portlandite. Also, don't forget the stoichiometric coefficients ratio. And then this will give you the amount of metakaolinite per gram of portlandite in stoichiometric reaction. And if you multiply by the amount of portlandite in cement, we get the amount of metakaolinite per gram of cement. And then we just divide by degree of reaction, and we get our mass of metakaolinite needed for full reaction if we have degree of reaction of metakaolinite for 0.4. So now we can again write this equation here. Let's put our molar masses. We already have the suggestions. He even suggests the whole equation. So we can accept. And then correct if you need it. So the molar ratio of metakaolinite to this one, that's correct. And we still need the stoichiometric coefficients. So 3.3 divided by 1. This is missing. This is here, 3.3 and 1. And then multiplied by the mass of portlandite and the degree of divided by the degree of reaction of metakaolinite. So this will give us the mass of metakaolinite per gram of cement. And now we just need to do the ratio, the replacement level, which again just copy this variable here, which is the solution of this stoichiometry. And we said we have 1 plus so this will be the replacement level. It's the mass fraction. The unit is mass fraction. So from 0 to 1, and here we have the unit of gram metakaolinite per gram cement. And now we can run all. We get some error. Let's check. We forgot the multiplication sign here. So we can even, let's see what the AI, how fast does it take? It's easier for me to correct it. But just here explain error, and then the AI will also, even if you don't see the error. So here now he's suggesting what you should correct, and you say accept and run if you agree, and then we have the solution. So all the debugging you can use the AI, but you should always check what he's suggesting, of course. So a note, this is a simplified metakaolinite reaction. We have this ratio, stoichiometric ratio. So if you adopt different reaction model, or you can include also additional hydrates, you will get different stoichiometric coefficients, and then you can set that accordingly in your model. And the lower the degree of the SCM means that you need more SCM. That's why we are dividing here by the degree of reaction, which is the fraction 0.4. So basically you are multiplying with the factor almost 2. So you need more SCMs if less of it reacts. So with this we finalized our model, and then we can again compare with, so how much we get? We get that we need 38%. Replacement of metakaolin will fully consume portlandite. And now if we go back to our slides, we can compare with TGA measurements, with experiments. And you can see exactly, yeah, of course, maybe I just, I knew it before, that's why I put 0.4. But yeah, this exactly fits the experiment. After 56 days, there is 0, this is the experiments done in our lab. We measured for Portland cement 1, replaced with 40% of metakaolin. After 56 days, we crushed the paste sample, dried it, put it in the TG, measured the TG, and this is the result. And now you can calculate all these points. You can, with the method I just showed you in Python, you can calculate the degree of reaction of metakaolinite. Any questions? But what I told you earlier, yeah, just use instead of the reference cement paste, I would do replacements, different replacements also with sand, with quartz sand, because you have the filler effect, which is not really maybe the same as metakaolinite, but it's still good enough, better than without sand, you know. So this, let me, maybe you are confused by this plot. Let me draw you. So the TG results. Let me draw you with time. I think you are more familiar with time plot. Also so if this is the, you know, the TGA. So it's percentage of portlandite. And if you have, you know, we have the reference cement, the portlandite amount increases. You are probably measuring in 1, 3, 7, 28 days. Yeah, maybe it's not, let's say it's logarithmic space. And then, so this is the Portland cement. So this is Portland cement reference. But if you would use, you know, the Portland cement with filler, let's use different color, green one. Like this is the way you should do it. Then you would get faster reaction, the filler effect, especially at the beginning. At the end, probably similar. So this would be your Portland cement plus, I don't know, let's make an example. I don't know, 30% usually with metakaolinite, 30%, but usually this is mixed clay, 30% of quartz filler. Or maybe if you do, you know, maybe the good reference would be Portland cement with limestone. But okay, let's keep now this example. And then when you add metakaolinite, actually that would be the green, but let's keep it lila. That would be grid cement, huh? So now we have our Rutolanic reaction. So let's say it's a bit less. And actually it's quite fast. So let's say it goes down fast. Metakaolinite reacts fast. What was here? So this is our Portland cement plus 30% metakaolinite. So we see our primary formation of Portlandite and then consumption of Portlandite. So this is then this difference here. Where am I? I'm here. This difference here, this is the Rutolanic reaction. And you can see this difference is different here than here, if you would have Portland cement without the filler effect. Here maybe not so many. Yeah, later the difference is not so important. But at the beginning, the difference between filler effect, reference, and just Portland cement without the filler effect, it can be a big difference. So this now allows you to model the degree of reaction, Rutolanic degree of reaction, using just TGA. And now you can model it. And there are not many papers in literature that model this, so you can do it now. So any questions? Very simple stoichiometric model in Python. You just need to a little bit to extend it, and you can do this. Your PhD paper. Yeah, you just need TGA, nothing else. And it's very realistic because all other all other methods like R3 tests, they just simulate with Portlandite solution. They are just, this is the real mixture with your cement. So this is really what you get in your mixture. Real Rutolanic reaction. And you can quantify it. I think it's amazing. Ready for you to use it. Any questions here?
Well, are these relevant only for Portland porcelain cement, or is it same? I mean, can we match this with other cements?
You can also do it for other cement, yes. But which type do you think? Do you want an example?
Well, we have specialty cements now, which are used in coastal zones with the glass fibers mixed in them.
Mm-hmm. Yeah, you can also see. You can see. You can also do it for other cements. I don't see any. You just need a reference. I mean, you are just wondering how much of that SCM reacts compared to the reference. And maybe even that reference already has some Putzlanik reaction, but you are still your main. You are calculating how much it reacts compared to the reference. Yeah, I think it's possible. Yes. And the reference can be already something Putzlanik. Yes. Or any type of, I don't know, it's the limestone or cement, or you can, yeah, why not? Why not to add fibers? But do they also react? Probably not so much putzolanical, yeah. It's only surface, a little bit reaction. Yeah, you need to mill it to have a high surface area, to have putzolanic reaction of glass. If it's a fiber, yeah, then it's only a little bit on the surface. Yeah, no problem. You can add it. Yes, exactly. Any other questions?
Hi, sir. Hello.
Yes, please.
Sir, will the trend be similar if we are using biomasses as supplementary cementitious material like rices, cash? Um,
Yeah, this is rice cask ash is like a silica film. I mean, basically it's a silica, reactive silica, very high surface area. So you can exactly model like silica film. But there you need to, yeah, the calcination temperature is important, the burning.
okay.
Yeah, there is no, I mean, at the end it's just reactive silica inside. Maybe you just need to change how much of that silica is really reactive in, and then you can also model it. Yes, it's exactly the same example actually with silica film. Yeah, very nice question. Thanks. Any other question, comment? Yeah, from the TGA, you know how to calculate the Portlandite content. It's just, again, the ratio of the water, because the water goes out. So you are basically asking the mass loss is because the water is lost from the Portlandite, or in this case, from the metacolonite. So again, the ratio of the molar masses and the stoichiometric coefficients. And then you have the theoretical mass loss of Portlandite or metacolonite in this case. And then you just compare it with your experimental mass loss. You should use the tangential approach. That's all explained in that book I showed you yesterday, the microstructural characterization of cementitious materials. There you have a chapter on thermogravimetry, and there you have it described how to use the tangential approach to get the mass loss, and then you get your result in percentage. And you should actually be careful, because usually the mass, how you calculate the, you know, if you do result like this, like it's calculated here, you are basically calculating, you get the result in gram per Do you know how much? Per gram of what? So in this case, you get the grams of metakaolinite per gram of your initial sample, your initial mass. So this is a gram per gram of sample, which you put into the into your TG. So your result here will be gram per gram of sample, initial sample. So this is the unit. But better way would be actually to, because the initial sample is very vaguely defined. It depends on the moisture content, especially for cements. That's also described in that nice chapter in the book, Material Characterization for Cementitious Materials. So better way would be, let me put it here, so that you get it gram per gram of cement, let's say, if you have cement, but or per gram of calcined, or how to call it, per gram of burnt sample. How to call it simply? Mass loss at ignition, ignition sample. I would call it mass per anhydrous. Let's call it anhydrous, yes, anhydrous. This is basically cement. You know, if you have, if you use cement paste, if you determine the amount of portlandite per gram of cement, and how will you determine by per gram of cement? You actually need to take the, you should divide or multiply. I don't know now. You figure out. you should just take the mass loss on the. Usually I took the mass loss at 1000. But actually, it's even better. In that paper, in that book, they suggest mass loss at 600, I think, because then it depends. Do you want to include the carbonates or you don't want to include the carbonates? But I don't like to include the carbonates. Now I forgot why do they suggest 600, but if you divide or multiply by the mass loss, so by this this factor here, 0.93. There is an easy way, engineering way, you can determine is this, you do need to multiply or divide, is that if you have, so if you release water, you have more concentrated system, so you should have a higher amount of portlandite. If you normalize it by per gram of cement, then because here you have also water. If you normalize to the initial mass, you also have water, so you have less. You should have less portlandite, and that means that you should here you should have more. That means that you should divide by the TG mass. This is how you should always think as an engineer. Should I have less or more result? So you should divide. You just divide by the TG at 1000. If you divide your result by the TG at 1000, you will get the gram per gram of anhydrous, meaning the gram per gram of cement. You can check also this in the book Characterization Methods for Cementitious Materials. This is really a must to have book for characterization of cementitious materials. You have the colorimeter, NMR method also. Of course, you don't need it. And I also don't need it. Then you have the MIP, the mercury intrusion porosimetry. You have XRD methods, describes how to do it from Ruben Snellings. You have the TGA, Barbara Lottenbach wrote that part, the chapter on thermogrammetry. And there are a few more methods. There is also a method how to stop the reaction, hydration, colorimetry, XRD, TGA. Yeah, those are the methods described in detail, how you should measure it. Any questions? Let me check if I missed something from the calculations.
So we have one question.
Yes.
The participant side.
Yes, please.
We have been discussing about hydration of the cement. I just wanted to know whether the same type of modeling can be applied for the using TGA for the carbon dioxide uptake in carbonation and decarbonation cycles.
Yes, excellent question. Yes, you can apply the same type of techniques.
Majorly, we go with TGA analysis for quantifying the CO2 uptake.
Yes. Exactly. Let me just show you. Yeah, maybe here. So between, usually if it's calcium carbonate, it will be, 800, around 800, the mass loss. But you also have
Yes,
the
sir.
amorphous calcium carbonate, especially
Yes, sir.
from the hydration carbonation. So it will be lower, 700. And then you can again do the stoichiometry, how much CO2 to the amount of CO2 to the molar mass of calcium carbonate, and then you can determine how much carbonates you have in your sample. This is approximative method, yes, but it works quite good, actually.
Okay, sir. Thank you so much.
There is a TC committee, technical committee, RILEM technical committee, led by Thomas Mace here in Germany, in Aachen University, and Ruben Snellings, exactly. They are chairing this technical committee on carbonation, and they discussed a lot and wrote, I think, some recommendations how to measure calcium carbonate. How to measure carbonation, yes. So you can check some results from this technical committee, the RILEM technical committee, TC, on carbonation. Any other questions? On paper. This one. We did some study on carbonation. This is for the geological CO2 secretation. So it's under supercritical CO2 conditions. And also those are for the oil wells, you know, to store CO2 in the wells, oil wells. And then the CO2, how it reacts with the materials. So it was 7 megapascal CO2 at 100 degrees. It's near supercritical conditions. It was a case study for Croatian wellbore condition, and the company, it was a Krosko company, the drilling company. They did this study, and this guy also did a PhD in this. And yeah, they are different. They use glass spheres because of the density for the mixture. And then we did a thermogravimetry study, and basically it's exactly how we quantify the calcium carbonate content. And you see here, you divide by the TG at 1000, and I took the values from 700 to 900. This is what I recommended. Shouldn't this be other way around? Yeah, but and then maybe I can show some TGA curves. This I will show you tomorrow. This is how, you know, all this calcium carbonate filled all the pores on the cement paste. This is the surface level of the sample, and then calcium carbonate basically filled all the pores, even the big pore, the air bubble pore, everything filled with calcium carbonate. Because this is the CO2 under pressure, you know. I think it's here. Supplementary file. Yes, you can see the TGA curves, and this is the part from 700 to 900. This mass loss was we attributed to CO2 carbonates. Yeah, we also saw some aragonite, water-ionite, and calcite, so different polymers. And different depths actually show different polymers of calcium carbonate, yes. Calcite, aragonite, and waterite. I think on the surface was more metastable waterites, aragonite, and in the inside was more calcite, if I remember correctly. Actually, yeah, okay, that equation was okay. Now I know why. Because here, you know, you have this is the theoretical mass loss, but then you have to divide this by the experimental, or no, experimental you have to divide by the theoretical, and then you get the inverse of this. That's why this was not a mistake. This is a correct equation.
Sorry to interrupt you. I had one more query seeing the XRD graphs, sir. We have been trying carbonation with different pressures, and if we see the XRD results, the peaks have not shifted much, but there is difference in intensities. Can we attribute this to the carbonation?
But do you see this calcium carbonate peak?
Yes, sir. Calcium carbonate peaks are there, but the major peaks they have not shifted much, but there is difference in the intensities.
Yeah, the intensity shows you it's proportional.
Actually, it was natural limestone. It was natural limestone and pure lime, which we tried for the capture of carbon with different pressures.
I mean,
for the
XRD is a semi-quantitative method. You can quantify, but then you should use Rietveld refinement method.
So are there any softwares for that? Rietveld
Yes.
refinement?
Yes, there is one freeware. Now I forgot the name. There are softwares available, yes.
Is there any reference material to study how Rietveld refinement can be studied?
Also, I think in that book, what I told you from Scrivener, that there Ruben Snellings also describes the Rietveld refinement exactly.
Okay.
I think it should be, yes. But even if you, I mean, if you do, most important is the do ratios. So if you have a standard, you should see how you should not compare directly the peaks heights, but you should compare the ratios of the intensities.
Okay, sir.
Yeah. Let me check this book. It was in the first slides I showed the book. I think it's even available in that link. Let me pay one. It's here. If you go to this is the book I'm talking about. Scrivener,
Okay,
Snellings, and Barbara.
Okay, sir.
This is really a must-have book.
Okay, sir. We'll look into that book. Thank you so much.
And if you go to here, this link, I think I even have a available link. Let me just check. Is this one? Ebook.
Okay. Microstructure.
Yeah, you need to buy it. Yeah. Colorimetry, sample preparation. Chemical shrinkage also. Spacer chapter, X-ray. Quantitative phase analysis.
Okay.
Maybe it's not Rietveld, but it gives you these ratio methods.
Okay.
So any other questions?
I know, sir. Thank you so much.
If not, we can go, I can go, let's go through the kinetics, because we have these files, Python files. So let's try to go through them. Yes, this is the kinetics. And if you want to go from the degree of reaction to predict in time, you have to solve this ordinary differential equation. And this, I made a simple code in Python that basically you just differentiate by finite differences. This is also exactly the way it's done in Games app and also in Heimerstruct. So you need to discretize this equation. You just convert this d to delta, and then so the next alpha is you calculate from the previous value of the alpha. You increment by delta t step, and then you have this function here, which is basically the same as this function here. and you take alpha from the previous time step. So this is finite difference method, the Euler method, the most simple Euler method. I will also show you how you can do more advanced Runge-Kutta method, and you can use this in Python library, how to integrate alternate differential equations using the powerful solvers from Python. So this is what I have in 2 more Python files. So basically you just, you need to define very small value just to kickstart this, and then you can calculate, you just propagate, you enter the loop, you increase the index value, and you calculate the new value based on the old value. This is the length of t, so you want to integrate for the total time period. You have the delta t step, and then you are just calculating the new value based on the old value plus the delta t step, and then this function value, which gives you the slope. So this is basically the slope. If you multiply by delta t, you get the value, the epsilon value. So this is the basic Euler finite difference method. So I made a code for you that you can implement this. And then we can use the same approach. Here you just plug in, the delta in j value. This is the basic kinetic rate equation from the Heimstrack. I removed all the omega factors. I included the Arrhenius, the diffusion, the dissolution. So you just define the parameters, and then you need to enter the loop because you want to solve for all the how the penetration front of that red part, how it shrinks, how that develops with time, and then you just write. So this is the equation you see. This is also if you would do ordinary differential equation, but this is already discretized. And then you can calculate the new time, the new depth as a function of the old one plus the delta t step, and then this function. And this is exactly what you implement here. So we have this function here. Just you need to just copy this part in the with multiplications and all the parameters which you define here. Exponential, and then you can easily do the integration, time integration. And after calculating the delta in, you can calculate also the degree of hydration. And this is based on the sphere approximation. This part I didn't actually explain, so I will explain. This part I explained quite well. And this part you can see here. This is the equation, how you can calculate. It's based on the sphere, sphere volume. How you can calculate the degree of reaction based on what is the penetration front. You see the third potential, it basically comes from the sphere. Maybe I have these calculations, I think here. Yeah, if it's a flat surface, this is how it would look like. But if it's a sphere, because of the volumes, then the degree of reaction, here you just do the ratio of the how much is penetrated divided by the total. It's like with the heat, total heat, you can just calculate the degree of reaction, it's linear. But here, if you have a sphere, you have a nonlinear behavior, and basically from the sphere equation, you can easily then derive this kind of reaction. You can see it also in the book from Van Breugel. I also put it here, the link to the thesis of Van Breugel you asked for. Here you can download it. So when we do this simple sphere calculation, we can calculate the degree of reaction as a function of the penetration depth. And here I just added this threshold thickness. If that penetration depth is bigger than the threshold, then you convert the lambda, switch the lambda from 0, which is initialized as 0, is you switch it to -1, because then this When it's 0, this you don't have any influence, this is just 1. So there is no, the factor is 1, there is no effect. But when you enter the diffusion mode, if you reach some threshold thickness, you basically switch this to -1. So then the thicker the shell, the more you reduce. You have a factor which is less than 1, so you are reducing your rate equation. And this is the diffusion, fundamental description of the diffusion, but for the planar case, which is just an approximation of the sphere. So you can improve this if you take the better equation for the sphere. But no need to improve, because anyway, this is just an approximative model, because yeah, anyway, the nucleation and growth, what we saw, is actually the most important. There is many reasons why this actually approximation is good enough. And if you run this code, this was, I show it in MATLAB, this you can run in MATLAB. Very simple code, you just define some, scalars, some parameter values, and just run this simple loop where you implement this integration of this kinetic rate, and then you calculate the degree of reaction, and here you have this switch of lambda, so very simple code. I will show it later in Python also, and show you also how you can use Python library to do the integration, so you don't have to do your own integration. And if you run this code, you will see this result, that how the shell thickness over hydration time, how that it evolves. So we have the penetration thickness, the red part, how much of the cement is consumed, the outer shell thickness, and the total shell thickness, which is the sum of the inner and outer. I think here we had the particle was 1 micrometer radius, so 2 micrometer diameter, and then we can see how the shell thickness evolves. So we have 4 micrometers plus 2 micrometers. So the expansion factor is 2 here, which we know from the 2.3, but this was not, the degree of reaction went till 55% degree of reaction. So here we can see how the degree of reaction of this small particle evolves with time. You can change the parameters, you can change the threshold thickness, you can change the constant for this solution, or the size of the particle, and then you can see how this also is changing. So now if you open again our teaching material in the Google Drive, yeah, here is the link. Just press the link. So we are in codes, day 2 codes, and then we go to reaction kinetics. First is the autocatalytic Euler reaction, and we need to fix the equation. So this shows you how to implement, first I will show you how to implement Euler method, finite differences, and then I will show you how to implement Runge-Kutta by using the Python library solver initial value problem. So this is the Python by powerful Runge-Kutta method, which is a 4th order method. That means it's a 4th order accuracy. Euler is only 1st order accurate, and this is the 4th order accurate. So it's much more accurate. If you have, the time step is delta t, to the power of 4 and you have very small delta t, so it's very accurate if you have power of 4. And Euler method is only first order, so the delta t on the first power accurate. So you should always use better accuracy if you want better. But I don't think these methods are, I think Euler in same games you have first order. Euler method also, Heimerstrack had first Euler method. So this is also, it also works fine. But in numerical methods you should always go for higher order accuracy. So here I am explaining now the, so we are implementing, this is the autocatalytic ordinary differential equation. So the rate, the degree of reaction rate is proportional to the concentration of the degree of reaction and of unreacted part. So we will get that symmetric bell shape of the curve. And here we just then define the parameters. And we also, let me just show you maybe easier, because this is actually quite simple. It's just this part. We just need a loop, and then write this equation, and then you get this symmetric shape of this autocatalytic kinetic model, which when you integrate, you get also the time dependent. So you can go from the model, you can go to, for example, to the colorimetry results. And also what I showed you, you can go back from the colorimetry results. If you divide by the total heat, you can go to this kind of representation where you have the rate as a function of degree of reaction, because this is what you need for the models. If you want a fundamental model, you should have degree of reaction. You should not have time in the model. So this is the equation what I'm explaining now, how you can integrate this in Python. So we just define the time step, the kinetic rate constant. Then we have the vector of the, this is called discretization time. So vector of time, if we start from 0 and we end up with 200, and we have step of 0.5 seconds or hours, depending on the unit of K constant. And then, yeah, we need to initialize the degree of hydration. Well, it's more number, maybe to the power of 9, because it will, then we need to calculate the rate. We enter the loop, so we go for every I, and we are calculating the new degree of hydration based on the old one. And this is where you now need to calculate this rate. And if you go to the slides, you will see, can you see now the slides and Google Colab? I hope yes. Now you can write this, basically we just need this to write this equation. But we need to use the variables we used here. So it's the degree of hydration on the previous time step, which is -1, I -1, index -1, plus, yeah, you can use j plus 1 j, but if you have here I, you can also implement like this. I did it here like this, but now here I am doing the I, then I go I -1, because here we start with 0. Here the index should be 1. And then we need, let's see what he's suggesting already. We have the k constant. We are just yeah, I forgot to write here the k constant. Here we also have the k constant, and we can have the surface area. So the k constant times the degree of reaction, previous time step, and 1 minus degree of reaction, also previous time step. So this is the equation you should write, which is exactly what you see here when you do transform these to deltas, and then you just explicitly you can calculate a new time step based on the previous ones. So this is what you should write in your code. Hope you can see it. I will leave you a few minutes so you can write it, so that you have the right code. Try also to do the degree of reaction. This one. You can already see the equation here actually. This is the degree of reaction. It's just the new one is the old one plus the rate times the delta T. Then you can calculate the degree of reaction. So you should put this equation here. Maybe if you just type degree of hydration here, actually, does it also suggest for you? Because I deleted it and then he remembers it. Remembers it. Do you also have this? Then you can just accept. Then you have the full solution already. So the program tricked me. Do you have this solution? If not, you can just type it from here. And then if you run everything, you should get no errors. Here we have, okay. And then you see your solution. So now you enter the time domain. Now you can compare these results with the calorimetry. This is also integral. And this is the model which is in degree of reaction, because this is the main state parameter. And then you need to integrate to know how that would, you need to solve differential equation to know how that looks in time domain, because you basically know the rates, you know the slopes of the curves, but you need to go, time per time step, integrate it to know how that then looks for each time step in each time. So to get this curve, you need to to solve differential equation, because this is usually the case in modeling. You know the rates, and you don't know the integral time, how it looks like. Also, when you work with I don't know, in physics with speeds. You know the rates basically. You drive the car, you know the rate, but you don't know in which time point you were in which space. So I don't know. You drive from here, from Frankfurt to Aachen, and in each time point you know exactly the rate, and then at the end you need to integrate to know in exactly which time point you were in which location. So you need to solve this differential equation to know that. And this is very usual in science, in all mathematics. You always know the rates because they are fundamental. They are the driving forces, you know. Also what I told you in kinetics, the driving force is basically the rate which depends on how far are you from the equilibrium. So this is the main fundamental driving force. And this is the main fundamental model. And to solve that model, you need to solve this differential equation. And then you know, and then you can compare this with your colorimetry results. This is why you end up with differential equations, and that's why you need to know how to solve them. This is why I'm showing you this, because this is you will end up always, when you start to model, very likely you will end up with differential equations. And tomorrow we will talk about diffusion, which is also partial differential equation, where you have the derivative in time and in space. Then we need to solve, and for chloride ingress, we need to solve the diffusion equation, so partial differential equation. So this is really, as an engineers, you have to be able to solve differential and ordinary and partial differential equations. This is if you are not an engineer if you don't know how to solve it. And here I explained you that you can use, very powerful Python toolbox. Actually, you just need to use Python to learn Python and use the toolbox, which already has a built-in function that solves the differential equation. So this is the built-in function in Python. You just need to call this solve. So this is, you can see the function definition. You just need to define the function you want to solve, the differential equation you want to solve. You need to define the time span, the initial condition, because every differential equation has its initial condition. Partial has also a boundary condition. And then you can define which method. Here is the Runge-Kutta method. And for 5, this is the, if you take the the computational method course I showed you, we have in the RILEM course, then we teach 5 days course only on numerical methods. So basically you just need to know how to define the function, which I learned you yesterday. Call that function here. This is the function. You need to define the time, initial condition, and you have the solution. So in one line, you can solve differential equation and use the most powerful solvers. They are in Python. So you don't have to actually learn how to solve it. You can just need to learn how to use it in Python. Yeah, then we just extract the solution and we can plot the solution. But here I made one fixed file because here in the definition, we need to, we call the function. This is the name of the function, autocatalytic order. So this is, we need to define the function. You remember from yesterday, just define the function name, input parameters, time and the degree of reaction, because this is the function we want to solve. It should look like this. So we need to provide this function. We integrate also with time. So we need to provide him also the time discretization and initial value. So that's why it's also a function of time. And now we just need to, define the rate parameter and here define our function. If you start typing, maybe you get the function directly, like last time. Let me check. No. Okay. If you start with k, no, it doesn't. So it's k multiplied. Actually, it shows. Yeah, here it shows it. So it's k multiplied by the degree of hydration, 1 minus degree of hydration. You just need to exactly. So this is the nice way even of this method. You just copy paste the function from your differential equation. You just need the function, and he's solving, he's integrating this, so you don't have to do like we did it before. You had to discretize it, and then you need to do this extra part. But here we really just have to write the function. Yes. Can you repeat? Can you repeat again? I didn't understand. There was an echo. Well, can you repeat the comment or? So we return the rate, and then if you run this one, you can then finally run also that one and plot it. And now we get our solution. So if we run everything, we get our solution, but there is one mistake. Maybe this is what you were saying, huh? Let's see, why is this different than the other one? We did something different. K01. Here, we need delta T, exactly. Oh no, here is the delta T. Do you also get result like this? So this one is much slower. I don't know why. Something is different. I wanted to compare, you know, the Euler method and the Runge-Kutta method, and they are quite similar, but somehow there is a difference between the two models. But now I cannot see the difference. You should get very similar results. You should get result like this. I don't know where the bug is now, but this is the results. The Euler method is very similar to Runge-Kutta. Let me do one last check. Yeah, looks everything okay. But somehow K is the same. Yeah, I don't know. Yesterday in the main file I got the same results. Almost the same. I don't see where is the error. Yeah, it doesn't matter. I hope you get the right result. If not, don't worry. The main point is that You can use the function, define the function very easy, and then in one line you can solve the ordinary differential equation. This is the main point. And now we can go to the growing shell model. So if you open the next file, let's try to fix this one. Then you will have a single particle growing shell model following the Heimstrack rate equation. This time I use the Euler method. So this is the equation. This is delta, and that means that the new one is equal to the old one plus this here, which is basically this one is the slope. And then we have these equations, which we can now implement. It's exactly following this Octave file over MATLAB. You can also run this in Octave and MATLAB, and then we will get these results. So let's now see it in Python. You just define input the libraries for vectors for plotting. We define the time discretization vector from 0 to 500 seconds in 1000 steps. We define the delta t, the step size. We just put the parameters, the radius of the particle, 1 micrometer. So the unit is in meter and seconds. We have the volume of the particle, the k constant, which is then in meter per second. We have the threshold value, threshold thickness to trigger the diffusion mechanism. This is half a micrometer. You can play with this, change it. And then we initialize our solution vectors, activation energy parameters. And then from the stoichiometry, we calculate the mu expansion, so 2.3. If you want to simulate the C3S reaction, you can simulate any other reaction, then you should change the mu factor, which you should model based on the stoichiometry, which I showed you yesterday how to do it. And then, then we enter the loop, the Euler calculation loop. And this is just, if the threshold thickness is reached, and the shell thickness is the outer shell plus the inner shell. If this is bigger than the threshold thickness, which is half a micrometer here defined, then we switch the lambda parameter from 0 to -1. And then this factor becomes important. And now we enter the main equation, and here we need to fix this. And here you already know that this actually should be in the previous time step, right? So simply just like this. And here, also very easy. So this is the slope, and we should multiply with time step. And the time step is delta t, dt. Now we can run. If you have many sessions open, you just need to terminate other sessions, close it, and then run again. Yeah, we have it. You can run all. And then we get this plot. We have the results. So now you have the single particle shrinking growing shell model for single particle hydration. Any questions? I hope you managed to do this in your Colab file. Yeah, just ask any questions. I'm open for questions. Let's check the time. But we started late, so we can have some more time. We can go for discussion questions, or I can also show you the TEM games from yesterday, how we can simulate pozzolanic cement systems. We can take an example of LC3 system, for example. Yeah, just ask, just interrupt me whenever you want. Ask me question. In between, I will open the TEM gems. Too many windows open. Seems like I don't have it here. So you remember from yesterday, if you go here to TEM Games app, then you, most important here is the tutorial. You have the videos. So you can in 1 hour, you can very well model. Like the models you see in, CCR publications, in 1 hour you will be able to do this. Just to look at the videos and you can do all these models, and you can do the models for all these systems. So for LC3 systems, all the blended cements, you can do any kind of pozzolanic. Raskaic-esque, very easy to add actually inside. You have even calcium sulfide aluminate cements, calcium aluminate cements, different types of cements. So let's take the LC3 system. We equilibrate. We can see our phase assemblage composition after 28 days. And if you want to change your SCM, you can add any kind of this, limestone, it's already there. This is the LC3 composition, gypsum 4.3%. Okay, nice, interesting. So this is the extra added gypsum from the SCM, because the gypsum should be also here in the cement. Yes, we have the anhydrite. 5.8, 5.9%, and there is extra added gypsum in SCM. Probably some clays also have gypsum. At least the German clay we burn, I saw that they have gypsum inside, because in this clays you have gypsum. But I assume this could be oversulfated, too much gypsum actually, system, oversulfated system. Yeah, I don't know how to, if you have too less, it's easy to add, but if you have too much, we should ask Zunina what to do then. You have too much gypsum. And yeah, you can add slag, you can add silica fume, calcine clays. This is 63% of calcine clay inside limestone. And we have, you can add fly ash. Yeah, I don't see any ash, but I would use silica fume for ash, and then just change the kinetics and maybe also the degree of reaction. Here they put it, it's fully, which is also never the case. It cannot react fully. It always has limited extent. So you can just change if you have, some unreactive part in your Rask hash. Just put, I don't know, you have 90% that will react, so you should just put 0.9 here. And the rest is not reactive, and this can be then your Rask hash. Yeah, for calcined clay, they put only 33% is reactive. So this is this type of mixed clays that there is only 33% of metal aligned, probably. Yeah, that's the typical LC3 composition with mixed clays, raw clays. And then you can also run the process with MPK. Now you know what this MPK means. This is the serial model for the kinetics, which includes the nucleation and growth, diffusion and interaction mechanisms. And then we can plot it, simulate process, and we can see how this get the kinetics phase composition of the full LC3 system, very complicated system, all the phases with time, how they react. It's really amazing tool, and everything is in few seconds running on the server, available for you. You can even download the Excel sheet, you can plot your results. So this is really valuable for your research, I would say. You can even have the composition of aqueous species with time, how the the pH and everything, how it changes with time. We can have the extent of reaction, so how the clay reacts with time. So by changing the kinetic parameters, you can change these kinetics. So if you have your Rask hash, you did your TG measurements, you know your reactivity with putzolans from the TG, from the calcium, from the portlandite content, then you can calibrate your model result, to fit your amounts of portlandite, which you can find here, which is the portlandite, this one. Where is it? Very little. This is the portlandite. Or, yeah, this one. So it goes up to, what is this? Like 2%, very, very low percentage of portlandite. Because we have, formation of this stratnegite and other phases. Probably you will get more portlandite in realistic systems, I'm assuming. And then based on this amount, you can then tune your reactivity for your putzolans. And then you can tune them by changing the kinetic parameters, which you can find in the simulation process here, in the MPK, and for each phase. For each phase, you have the parameters of the model, all the kinetic parameters. So for all the phases, it's quite comprehensive model. And here is for slag. They use this a bit different. It's more empirical model. And then you have 5 coefficients also that you need to fit. You can change the value of these coefficients. You can check here you can check the model, how it looks like. And then you can fit your TG experiments and you calibrate your model to your experimental results. Let me show you maybe in the tutorial. Yeah, here is the description. 5PL. they don't show the equations. I was hoping maybe they show they cite the papers where you can find the equations. Yeah, it's here, Lottenbach. But this is for modified Parat and Killock. Maybe here is one more citation we need. I think it's somewhere inside. You just need to see the. You need to go more inside the processes. Yes. Then you can fit those parameters and then you change your kinetics to fit your TG results, for example. You can take this one to, so you can link this maybe with your TG experiments. Yeah, it's a bit, I know, manual because you cannot run this directly in the Python code. So it's a bit of manual fitting. No questions? Yeah, I don't know. What are you interested in? Which material? Rice husk hash? Maybe some other? This is Slack. This is, let's see, what is this one? SEM2. I think this is Flash. STM. Yes, this is the Flash. SEM2B. And if you want to see a recipe, SEM3B, I think this is like STM. Yes, this is GGBF. Slack. And you have, what more is there? What did we, sulfate resistance. So this one has less aluminates, less C3A. And it's sulfate resistant because the aluminates, you know, it's the delayed ettringite formation. If the sulfates, if there is too much aluminates, then there is the ettringite which expands and then cracks the system. And you can see here we only have 0.4% of aluminates, but we have 22% of C4AF. Usually this is like 9% in cement of aluminates. So this has very low percentage of C3A. Calcium sulfoaluminate cements. So we have the yelenite, belite, 20% belite. And this is yelemite, 60% yelemite. It's the calcium aluminosulfate clinker. And if we equilibrate, we get gypsum and monosulfate mostly. Let's see. Yes, it's the gypsum stratlingite because we have also silicates and monosulfate. What is this? Aluminium hydroxide. Okay. Any more questions left? Yeah, now you can play with this. I don't know what else you could change. Simulate process. We can see the pH increasing because of the alkalis, releasing, and then decreasing because of pozzolanic reaction, probably. Maximum 13.35. So we have all the very high concentration of, this is just PE. We don't, if you want to see aqueous totals, then we should look at here. So we have very high concentration of potassium, of kalium. Then we have a lot of natrium. Then it's calcium. No, sulfate. Sulfate, a lot of sulfates at the beginning, and then there are precipitating etrigite. Then it's less sulfates. Here is probably monosulfate. Here is etrigite, I guess. Then we have the calcium concentration, and you can see how with time you can predict the pore solution concentration of your cementitious system. Even iron concentration, alumina concentration, it's increasing with time. Probably because of the reaction of the methacrylonide. Even carbon. So the carbonic acid. Yeah, I don't know what to tell you more. To change, yeah, you can change the temperature, water cement ratio, the mixture, composition of cement, SCM, water cement ratios, and then you can simulate everything as a function of time. You can even predict heat rates. Cumulative heat. Total amount of solids, how much CSH, you can see mostly it's CSH. Then it's the etrigite. This is the amount of reacted clay. Yes. So I'm open for your questions. Still. It was a long day for you, I know. 4:26. I think it's exactly the hour to finalize with some questions if you have. For steel slag, which cement type we have to choose? Excellent question. There is no steel slag, I think, inside because it's but I would choose the composition of the steel slag is you have C2S basically. You have the gamma C2S, and this one is actually not so reactive. That's why they don't use it actually. You should activate first the steel slag with I don't know, you can carbonatize or you can even add chemicals like you need to, steel slag is not reactive actually for using in cement. You need to reactivate it because the main composition of the steel slag is gamma C2S and some magnesium silicates, I forgot the name. At least that's the one that I worked with. Let me see the chemic. Is there no mineral composition of the slags? It's only chemical composition. Yeah, but basically it's gamma C2S. Which is not hydraulically active. Yeah, maybe there are some putzolans inside that would react, but mostly I know that you need to activate the still slag. Not so reactive.